Our next speaker is Mike Zaletel from Berkeley, and he's going to talk about skyrmion pairing DMRG evidence for topological route to superconductivity. Please.
Great, thanks. And thanks to Shankar for the invitation. It's always a pleasure to talk off Andrea Young as well, but I'll try and bring your attention back to twisted bilayer graphene for the remainder of this talk. And first I want to thank my postdoc here at UC Berkeley, Shubhayu Chatterjee, as well as Matteo Ippoliti at Stanford, who contributed to the work here. I think it's quite beautiful numerical results. And I also want to thank my collaborators at Harvard, Ashwin Vishwanath's group, for a lot of the theory ideas, which were the inspiration for this. Okay, so what's the outline of the talk? First, the first part, I'm going to review this lambda level picture for twisted bilayer graphene. It's going to have a bit of overlap with Ashwin's overview, but hopefully that's helpful. Then I'm going to get into the particular phenomenological model that I'm going to study with DMRG. And then finally, I'm going to walk you through DMRG evidence for why this lambda level picture of bilayer graphene actually supports the presence of superconductivity, entirely electronic in nature, mediated by the pairing of skyrmions. Okay, so what's the question we're looking at? We're going to be focusing on twisted bilayer graphene at half fillings, so fillings plus or minus 2 of the 8 bands. And to simplify this discussion, I'm going to assume that there's some form of flavor polarization happening at plus or minus 2. For simplicity, I'll actually just assume it's spin polarization. So there's other scenarios which are possible, maybe as a spin valley anti-ferromagnet, something like that. These other scenarios are talked about in these theory papers. They're not conceptually too different. So let's just assume it's spin polarized at plus or minus equals 2. And that means for the rest of the talk, I can just completely ignore spin in this problem and just focus on the 4 bilayer graphene bands coming from the valley degree of freedom and then the orbital degree of freedom, which gives the mini Dirac points. So what's the question then? Once we've narrowed down to 4 spin polarized bands, still at plus or minus 2, you need to pick how to fill 2 of 4 of them in order to form some sort of insulating state. So that's one of the first questions. And then the second is what happens when you dope this insulator? What are the nature of the excitations, and might they exhibit a pairing gap, which would lead to superconductivity? Okay, so the one starting point for thinking about this is to develop analogy between twisted bilayer graphene and quantum Hall ferromagnetism. And you can make this analogy fairly precise by starting from the chiral limit that Ashwin talked about, where you just artificially turn off the hopping between the 2 layers in the AA region of the Moiré pattern. Okay, so this was explored in a number of papers here, and it leads to a very interesting band structure where if you're right at the magic angle, you find that the bands are not flat, they're actually perfectly flat. And furthermore, because they're perfectly flat, there's different bases you could choose to identify the 4 states. Obviously, valley is one of them. But the other natural label for your bands is just the sublattice, whether it's on the A or the B sublattice of the graphene. Okay, so in this limit, it becomes natural to limit to label the 4 valleys by K and sublattice, and you have the 4 of them. And what you find is when you work in this basis, not only are the bands flat, they're actually churn bands. So in valley K and sublattice A and K prime B, they're churn 1 bands. And then if you apply time reversal or a C2 symmetry, or sorry, a time reversal that flips the valley and flips the churn number, so you get 2 churn 1 bands and 2 churn minus 1 bands. So conceptually, I'll often draw them as if I had a bilayer problem where the 2 different layers have opposite B fields corresponding to these different churn numbers. Okay, so once we have this analogy to it being like 4 Landau levels, we can go back to the problem of what happens at nu equals 2. You basically need to fill 2 of these 4 Landau levels. And of course, there's many different ways to fill 2 of 4 Landau levels. And the remarkable thing is actually in this flat band limit and assuming this chiral symmetry, there's actually an enlarged hidden, we call it symmetry of the Coulomb, which relates a bunch of different ways for filling 2 of 4. So some possible examples would be you could valley polarizing it, putting all the filling into valley K. You could do valley Hall, where you tie together what valley you're in and what sublattice. You could do quantum Hall, which would mean you'd fill only the churn 1 bands and not the churn -1 bands. Or you could do some more interesting things where you actually, when you put the electrons in, they go into a coherent superposition of the two valleys, which we'd call intervallic coherence. So that spontaneously would break the value 1 symmetry, which physically corresponds to some enlarging of the unit cell at the graphene scale. Now, remarkably, in this limit, you can actually show, and this is what we did in this PRX paper in 2020, that all of these ground states are exact eigenstates of the fully interacting problem with Coulomb interactions projected into the magic angle flat bands. Okay, so in the special limit, you have a bunch of different competing insulators at nu equals 2. And there's, if you have a bunch of competing insulators with different symmetry breaking, it's natural to try and develop a nonlinear sigma model picture for the physics of the problem. So the picture we develop is as follows. In the Chern 1 sector, you have these two bands. I'll think of those two bands, really it's valley, they're distinguished K and K prime, as forming a particular pseudospin. And then you have another pseudospin in the two bands with the other Chern number. So you can think of different types of symmetry breaking as just a specifying of these two pseudospins in the two Chern sectors. So just to relate that to the orders we saw earlier, if you want to valley polarize in both Chern sectors, you want to fill only valley K. That's like having both of these nonlinear sigma model vectors pointing at the north pole, and d equals 1. On the other hand, just to highlight another type of order, suppose you do have intervallic coherence. You want in one of the Chern sectors that the electrons go into a coherent superposition of K and K prime. So that corresponds to a vector which is ordering on the equator or the XY plane. And that gives these different types of IVC states. And in both cases, whether you're pointing at the North Pole or on the equator, there's two types of order. One is where the Chern 1 sector and Chern -1 sectors are pointing in the same direction. That gives valley polarization, for instance. And then the other possibility is that the symmetry breaking in the two Chern sectors point in the opposite direction. That gives valley Hall and a state I'll come back to, the Kramer's IVC that Ashwin also talked about. Okay, so in the chiral flat limit, all those states are degenerate. What happens when you put back in the fact that in the experiment there, of course, is some dispersion in the problem? So Eslam did a beautiful analysis of this perturbatively. You can treat Coulomb as the dominant part and treat the bandwidth as a perturbation, and then just like super exchange in the Hubbard model, do second order perturbation theory in T over U. So the effect of this bandwidth in this lambda level picture is it hybridizes the two different Chern sectors within the same valley. And when you work out what that gives in second order perturbation theory, you find that it couples the pseudospin vector in the Chern 1 sector antiferromagnetically to the pseudospin in the opposite Chern sector. So it's going to lower the energy of these states where the two arrows point in opposite ways in opposite valleys. Okay, so the magnitude of this inter-Chern antiferromagnetism we call J. Its precise value is sensitive to things like the angle you work at, because that affects the kinetic energy, but it's on the order of 1 to 2 MeV. Now, the second deviation from this this limit is that I need to turn back on the tunneling between the two A sublattices. We need to take the deviation away from the chiral limit. So if you work out the effect of this, what it does is it leads to, in this nonlinear sigma model picture, easy plane anisotropy, which prefers ordering to actually occur in the XY plane. So this easy plane anisotropy I can describe by this coupling lambda, and it just gives stronger coupling in the XY plane and weakens it in the Z axis. Okay, so altogether, this is the kind of nonlinear sigma model picture for the different orders that could occur. J, as I said, is 1 to 2 MeV. Lambda is something like maybe 0.5 MeV. And once you put these two effects together, away from the chiral limit and putting in the dispersion, that selects out a unique insulator for filling 2 of the 4, which is this intervallic coherent state in which the pseudospins are opposite in the two Chern sectors. And we call this the Kramer intervallic coherent state. So what is it physically? It's a magnetization density wave. So if you zoom in to the problem inside the Moiré, like at the scale of the actual carbon atoms, what you'd see is a Kekule-like current pattern of alternating currents, which lead to a small magnetization within each carbon unit cell. So this clearly breaks time reversal. It does actually preserve a particular combination of time reversal and a U1 rotation of the valleys. and that will play an important role in allowing for superconductivity in this model. So what's the numerical evidence for this Kramer intervallic coherence state? Ashbin presented really beautiful results on the determinantal Monte Carlo, which supports this. Here, that was at filling 0 of 4, so that's like the spinful version of the problem. We can also ask whether it occurs at filling -2 or 2, assuming spin polarization. And in this context, we're actually able to confirm that the intervallic coherence state is the ground state using density matrix renormalization group calculations. So for the input of this, we just take the BM band structure, and then we take the full 1/r Coulomb interaction, and we project it into the flat bands. That leads to a whole bunch of complicated matrix elements. You just evaluate all those matrix elements, and then you wrap the 2D problem onto a cylinder. The approach we take is we keep it actually k-space around the cylinder, and then we go to real space along the cylinder for certain technical reasons. But still, we're solving exactly, the just flat band projected Coulomb problem, and then we can throw it into an infinite DMRG and find properties of the ground state in any particular doping we're interested in. And the conclusion from this is that at ±2 filling, we find from DMRG that this model, the magic angle twisted bilayer graphene, is this Kramer's intervallic coherence state, so long as the heterostrain in the system is less than a critical value of about 0.1%. Above that, there's actually a phase transition into a semi-metal. So this is quite interesting because if you look at STM studies from Caltech and the Princeton group, et cetera, they're able to locally image the strain. And at least in their samples, they tend to find heterostrain, which is varying anywhere between, say, 0.5 and 0.2. So our finding here suggests having this phase transition between this insulator and the pneumatic semi-metal at this small value of strain, that what you see in a particular sample could easily actually depend on these small changes of the strain, which seem to be happening in experiments. So that adds some complication here that we, when you're looking at a given experiment, it might actually be quite relevant what the strain is. And this potentially could explain some of the disagreement between different samples as to whether there's a gap state at nu = 0. Maybe it's just different conditions for the strain. Okay, but at least within this model without strain, there's very strong numerical evidence at this point that the ground state is this Kramer's intervallic coherence state. Okay, the natural question then is what happens if we start out with this KIVC and dope it? So, one advantage of DMRG, we don't require particle hole symmetry or anything. It's just one line in the code that we change and we can dope it. Obviously, we're working on that, but it's very hard. As soon as you dope away from the insulator, the state becomes very entangled. So the computations just take a long time. They're running now, so hopefully the next conference we'll be able to talk about it. But for now, it's a work in progress. Okay, but in the meantime, the basic physics of this Landau level analogy suggests we could simplify a bit all the complicated physics of the Moiré system and consider a more phenomenological model where we just take this Landau level analogy literally. So instead of having 4 churn bands related by time reversal, 2 churn 1 and 2 churn -1, we're instead going to replace the Moiré length scale with a magnetic length and consider continuum Landau levels and say gallium arsenide. But we're with this weird setup where 2 of the Landau levels need to see a magnetic field going in one direction, and the opposite need to see the opposite magnetic field to realize the flip churn number. So that's the model I'm going to discuss for the rest of today. How good is it? Well, one of the most important things that we're going to be neglecting is that if you look at the distribution of Berry curvature in these churn bands, it's actually not uniform. So it's somewhat concentrated near the gamma point of the magnetic Brillouin zone. When we go to the continuum Landau levels, the Berry curvature is completely uniform. So that's one of the effects that we're going to neglect. But I can still think of it as sort of the spherical cow model of twisted bilayer graphene. It keeps the correct symmetries of the problem. It keeps the topology of the bands, and of course, we're going to keep the 1 overall Coulomb repulsion. Okay, so now let's dive into what exactly the model is. Every physics talk should have a Hamiltonian. So what's the Hamiltonian? Our model is going to be sort of like a quantum Hall bilayer. So we're going to have 2 spinful 2-dags. So the language I'm going to use is what in magic angle graphene was this churn sector, churn 1 versus -1. I'm going to call that the layer. That's going to be my index gamma. And then within each layer, I need to have this pseudo spin, which I'll just simply refer to as spin. So altogether, that gives me 4 component fermions. And then I need to encapsulate this physics of this antiferromagnetic interaction between the 2 layers. So here's the Hamiltonian. I just have quadratic dispersion, but you can see here I need to give an opposite magnetic field for the 2 layers. So that restores time reversal. I'm going to have a long-range Coulomb repulsion, and then I'm going to have the antiferromagnetism. So for the long-range Coulomb repulsion, even though I'm drawing it like a bilayer, the interaction is equally strong between, the interlayer and intralayer interactions are equally strong. So at the level of the Coulomb, it almost looks like it has an SU4 symmetry. Of course, there's not really an SU4 symmetry because the 2 layers see different magnetic fields. And then finally, you can measure the local spin density in the 2 layers, the pseudospin density, and then I'm just going to put in by hand an antiferromagnetic coupling between them, even though microscopically it arises from the super exchange method. And for the remainder of this talk, J is going to describe the SO3 symmetric part of that, and lambda is this easy axis anisotropy. And I need those 2 effects to account for dispersion and deviation from the chiral limit that we have in magic angle graphene. Okay, so this is the model. And the claim is the following. If you solve for the ground state of this model at 2 plus a small doping, it is a superconductor despite the long-range Coulomb repulsion for any J greater than 0. Okay, so I think this is quite beautiful. This is a entirely repulsive all-electronic model. And we have, because the topology of the churn bands, as I'll talk about, a mechanism for getting superconductivity. So what's the numerical approach? It's very similar to doing fractional quantum Hall numerics. So of course, if we just look at the single particle effect, for each of the 2 layers, I get a tower of lambda levels. Both of them are spin degenerate. And if I work in the limit of a large magnetic field, the cyclotron spacing is going to become larger than the Coulomb interaction. So I'm going to be able to project the problem into the lowest lambda level. Now note here that the lambda level spectrum doesn't really care about the fact that half of them are positive magnetic field and half are negative magnetic field. The way that the magnetic field comes into play is when you go to compute the Coulomb matrix elements, the 2 different churn sectors are related by complex conjugation. So there's some different phases in the wave functions, and that leads to different complex amplitudes in the matrix elements. And that little change, as we'll show, is actually what leads to superconductivity. Okay, so from here on, it's very similar to standard quantum Hall. I just take 1 over r Coulomb and project into these 4 lowest lambda levels. So at that point, we can actually apply tools that Roger Mong and I had developed for dealing with quantum Hall physics. We want to apply DMRG to it. So we take the quantum Hall problem and we put it on a cylinder using the Landau gauge. And Landau gauge has this cool effect that the orbitals are plane waves around the cylinder, but they're Gaussian localized along the length of the cylinder. And the way the magnetic field shows up is that for the churn 1 bands, the center of the Gaussians and the momentum are positively locked to each other, and in the other B field, they're anti-related. But nevertheless, it's just kind of like doing 2 copies of fractional quantum Hall with a flip between them. You arrange these orbitals into a 1D chain. You get a very complicated Hamiltonian, but still formally it's a 1D fermion chain, and then you can just throw it into the DMRG algorithms I developed with Roger and Frank. So what sort of problems can we handle with this? Well, it's extremely complicated because you have a 4-component system with a long-range Coulomb interaction. So we can't do quite as large as we could do for, say, single component fractional quantum Hall numerics, but it's still not a very thin cylinder. We can do circumferences of 8 to 12 magnetic lengths, which roughly speaking, you can think of as like, studying magic angle graphene with a circumference of, say between 6 and 10 Moiré spacings. Any questions there before that's the model and method before I dive into the superconductivity?
Yeah, Mike, this is Shankar. I have a quick question.
Yeah.
So this extremely demanding DMRG will tell you may tell you that you have superconductivity, but will it give you any idea about what the possible TCs? After all, electron-electron interaction leading to superconductivity doesn't impress me, because Kohn and Lettinger told me that happens, except, in their case, TC was very low. Does your technique tell us anything about possible TC?
We'll be able to measure the pairing gap.
Okay, all right, so I'll wait. Okay, thanks.
Yeah, as well as the mass. So,
all right. Okay, so you have some estimate. Thank you.
Yeah, so that's the cool thing. We can just get excitations energy here, and I'll show those. Okay. Yeah, great.
Like we do in fractional quantum Hall, so you can do the same thing here.
Yeah, exactly. Yeah. Okay, so what's the physics of this model? Well, first, by analogy to the nu equals 2 insulator magic angle graphene, we first want to know what happens if you fill 2 of these 4 lambda levels. And here it's not surprising, the physics is almost there by hand in the Hamiltonian. As we said, we had between the 2 quantum Hall bilayers, we put in this anti-ferromagnetic interaction. So naturally what it does is exchange prefers you to fill the system in a uniform way, just like an interquantum Hall ferromagnet. And the way you fill it is that in the churn 1 layer, you fill it with, say, spin in the x direction. And then because of this anti-ferromagnetic coupling in the other churn layer, you fill it with the opposite magnetism. So we get this XY type of order. So that's filling 2 of 4. It looks like integer quantum Hall effect, but because we fill 1 in a churn 1 and 1 in churn -1, the Hall conductances add, and overall it's just an insulator. Now, as Shankar was alluding to, this is like quantum Hall numerics. We can just compute the excitation energies. What you find is that the energy to add an electron on top of this insulator is twice the Coulomb scale. So it's a very strong, robust insulator. Now, how do I detect in the DMRG that it forms this XY order? Well, we can assign an order parameter, which is just the difference in the spin between the 2 layers. That gives this nail vector. There's a slight subtlety that because we're doing the numerics on a cylinder, at long distances, it's actually a 1D problem. And this XY order is a continuous U1 symmetry. So what we actually expect is to get algebraic order. And that's indeed what we find is we take the 2-point function of the nail order parameter along the length of the cylinder, you find algebraic decay. And as you increase the length of the cylinder, so you can see here we go from circumference 8 to 12, this fall off becomes slower and slower as you go to larger in circumference, consistent with this algebraic order actually extrapolating to true off-diagonal or true long-range order in the 2D limit. Okay, so that's our starting point, this XY antiferromagnet. What happens when we dope it? So I'm first going to show you schematically this sort of phase diagram we get before looking at the actual numerical results. For a typical small doping, maybe delta being a quarter, we can look at the physics as a function of the strength of the SO3, the J, symmetric part of the antiferromagnetism, and lambda, which is the amount of the easy plane anisotropy. And what you find is that there's always 2 phases. For large enough J, I'm going to convince you it's a superconductor. And then there's a first order phase transition. The precise location of it depends on what doping you're working at, below which the system is a charge density wave. At least for low dopings, though really actually what this low J phase is, the non-superconducting one, depends on what doping you're at. Like if you're at doping 1/2, you get a composite Fermi liquid. At 1/3, you might get a Laughlin state or other complicated things. But the main point is just that there's a superconductor for large J and then some other less interesting phase at low J. Now you'll note here that as lambda goes to 0, for a fixed doping, we find that the phase boundary, you only get superconductivity for lambda equals 0 above some critical J. But we believe that as the doping goes to 0, it's actually consistent with the value of the critical J eventually going to 0. And I'll explain why in a moment. So let's look at some actual data, or at least data that's pixelated. I'll walk through it, but we can define order parameters for the superconductivity, the XY ferromagnetism, and charge density waves. fix a particular doping. This is data at 2 + 1/4, and then just measure them as a function of these J and lambda parameters. And we indeed, as I advertised, find 2 different phases. So the superconductor, and then the low one is some coexistence of XY order in the charge density wave. So let me show you the evidence for superconductivity. I'm just going to pick a point up there. Well, of course, we want to know what the pairing channel is. And the pairing channel takes the following form. It always pairs together electrons which are in opposite Chern sectors or opposite layers, which are related by a time reversal, so it also flips their spin. So it's kind of like pseudo-spin singlet interlayer pairing. But then you can note here that it's not like P or D wave. The electrons sit right on top of each other. Okay. So that's the pairing channel that we find. And again, because this is a continuous symmetry, we can't just take a 1-point function because of Mermin-Wagner. Instead, we measure the 2-point function of the pairs along the length of the cylinder. We find a power law. So here's an example. The superconducting correlation function as a function of the distance along the cylinder, and you see beautiful power laws out to 10 or 100 magnetic lengths. There's one technical point here that, you know, DMRG really has some fixed accuracy, and you need to increase the accuracy of the DMRG to get better results. And as you do that, we indeed see for more accurate DMRG, the power law persists out to larger and larger distances, consistent with a true power law if we could do infinite accuracy DMRG. Okay, but how do we know that this superconductivity isn't just an artifact of being on a thin-ish cylinder, you know, circumference 10 or something? Can we show that it actually survives in the true 2D limit and is a 2D superconductor? Well, if there was a 2D superconductor which had some finite phase stiffness rho, you can do a simple calculation to predict what would that 2D superconductor look like if you put it on a cylinder. And you can show that the exponent of the superconducting power law on the cylinder needs to decay inversely with the circumference of the cylinder if it's a true superconductor. So that's the prediction for 2D superconductor. We should be able to see that this power law changes as you increase the cylinder of the circumference. So you can see this by eye in the data here. We look at a circumference 8 and 11 cylinder on a log-log plot, and you can see the fit for the power law shifts. It becomes slower decay for larger circumference. I won't delve into it, but you can develop this into a full scaling analysis. And we find that all our data across circumferences 8 to 12 collapses if we take an exponent for the superconductor of something like 10 over L, which is the expected form for 2D superconductivity. So as far as I'm aware, this is some of the first unbiased numerical evidence for all electron superconductivity that actually persists in the 2D limit, starting with Coulomb repulsion. Okay, what's the evidence for this charge density wave? I mean, that's much simpler. You can just measure the local charge density and you'll see it. I'll show you something somewhat richer because it's a little bit interesting. We can measure the density correlation function in the ground state. So I'm going to show 2 sets of data here. The top panel is just a real space picture along the cylinder of the density correlation in the charge density wave phase. And what you can see is that electrons are anti-correlated within a little like correlation hole. But then at larger distances along the cylinder, you can see there's this residual stripe modulation corresponding to the fact that this charge density wave is a stripe that develops. On the other hand, you can do the same experiment at larger J where you're in the superconducting phase, and you actually see, even though the Coulomb repulsion stayed completely the same, you actually develop an attractive hole around the origin and no evidence for charge density wave at larger distances, just by changing J. Okay, so that's the evidence for superconductivity in this phase diagram. But Shankar, that's a great question. How do you know it's actually what's the mechanism for it? What's the glue? And in the remainder of the talk, I'd like to walk through the picture we've developed for this, and that's that the topology of Landau levels leads the charge excitations to actually come in the form of textures in the pseudospin, skyrmions. And when large skyrmions are able to form, they effectively spread out their charge and can avoid Coulomb repulsion. And then the small weak antiferromagnetism, as I'll show you, causes them to bind into charged 2e pairs, which are bosons, and then we believe they condense. So that's the picture I want to go through, that the superconductivity is the result of skyrmion pairing. So before delving into that, I mean, Shankar is an absolute expert in this, but I think for the audience, it's kind of nice to have a bit of history on skyrmions and the quantum Hall effect. It's very beautiful physics. The starting point is, of course, quantum Hall ferromagnetism. So if you look at gallium arsenide, say, at low magnetic fields, you see an integer quantum Hall sequence that only appears at the even integers, consistent with the lambda levels actually being spin degenerate. Only at larger magnetic fields do you actually start seeing the odd integer quantum Hall effect form. And you might suppose that the reason it forms at large B is because you have a Zeeman field, which is splitting the up and down spin. But the numbers don't actually work out. So the Zeeman energy is something like 0.2 Kelvin per Tesla. But these odd integer quantum Hall effects are seen at temperatures orders of magnitude above that Zeeman energy. So what's happening here is not actually Zeeman leading to the splitting of spin, but it's actually interaction-driven quantum Hall ferromagnetism. And there's a beautiful series of works developing this from the 90s. So the picture is that even if you completely remove Zeeman, if you half fill a spinful lambda level, the system will just spontaneously pick a direction in the spin space and polarize. The physics here is just the exchange physics that Andrea was talking about. If you think about the Stoner criterion, you want a Coulomb scale to be larger than the density of states. Well, in a lambda level, the density of states is infinite, so it immediately just polarizes. But the result of this is that the gap for the integer quantum Hall effect at odd integers is not set by the Zeeman energy, but actually the Coulomb scale, which explains the high temperatures that it's able to be seen in experiments. So what's interesting about these integer quantum Hall ferromagnets? So locally, you can just picture it as indeed there's a spin, at each point in space, you have some spin polarization. It's natural then to ask what happens if you put a texture in that spin. So one type of thing you can actually make is a spin wave, but it was realized that there's actually a much more interesting thing, which is that you can put in a skyrmion configuration. And what you find is that due to the Chern number of the lambda level, if you look locally at the skyrmion density, this particular derivative term here, it induces a physical electrical density improportional to the Chern number. And as a result of this, if you integrate this relation, you find that if you put a skyrmion into the system, it actually carries an electrical charge, which is the product of the skyrmion number, whether it's a skyrmion or anti-skyrmion, times the Chern number of the lambda level. This sounds very exotic, but it's well established in experiments. For example, there's these beautiful NMR experiments from the mid-90s, which are able to actually measure the size of the skyrmions. And they do find evidence from NMR for the existence of large skyrmions in the integer quantum Hall effect. Okay, and this physics, I should also mention, generalizes to, say, quantum Hall physics of monolayer graphene. Sarma and Andrea had an important role of that, and there you can get skyrmions in larger order parameter spaces. Okay, so how could that apply to our case here? We, in a sense, have two copies of the integer quantum Hall effect, one from the Chern 1 sector and one from the Chern -1 sector. Well, the first thing you might think to do is just try putting in an excitation, which is a skyrmion only in one of the layers, one of the Chern sectors. Okay, so the topology is the same. So that would give an excitation of charge E. But the problem is, because of this anti-ferromagnetic coupling between the two layers, wherever you have the skyrmion, you need to unalign the two layers, and that's going to pay a penalty of J. So this ends up being a rather expensive thing to do. So what's the better alternative? Well, suppose I make a skyrmion in the Chern 1 layer and an anti-skyrmion in the Chern negative layer. So when you go from skyrmion to anti-skyrmion, that just corresponds to applying the antipodal map, where you just take the pseudospin and you just flip it. So naturally, if you make this configuration, the two layers are always anti-aligned, and so the J term remains completely happy. Okay, so this would be good from the point of view of J. But what's the charge of it? Here's where this peculiar flip of the magnetic field comes into play. So since charge is Chern number times the number of skyrmions, I've made a plus skyrmion in the top layer, and that's a churn 1 layer, so that carries charge 1. And I made an anti-skyrmion in the churn -1 layer, so 2 wrongs make a right, and that also carries churn 1. So this composite object, if it binds together, is actually a charge 2 boson. Okay, so at a topological level, you could have these skyrmions, but does it actually happen? In reality, you have competition between 2 effects. There's a 1/r Coulomb repulsion, which is very strong. It's the dominant scale in this problem. The J is something like 1/10 of it in most of the phase diagram we're looking at. So obviously, if you have long-range Coulomb repulsion, it doesn't want these 2 chargy skyrmions to sit on top of each other and bind. It wants to rip them apart. On the other hand, as I discussed, the J would prefer these excitations to sit on top of each other. So who wins? The way we want to quantify that is to measure the pairing gap, which would be we compare the energy to make 2 well-separated electrons relative to the energy of making 2 electrons which are allowed to be close together. And if you find this is positive, it means that there's a pair binding energy, which suggests that the lowest charged excitations are actually the charge 2 objects rather than individual electrons. So as I'm going to discuss, we're actually going to be able to measure this pair binding energy. So we do it in 2 ways. One, to establish that the skyrmions are there, we can actually analyze just semi-classically a nonlinear sigma model description of the problem. And then 2, we can just use DMRG to find the exact quantum eigenstates and just measure the energy of the excitations. And then we can compare those. That's what I want to walk through here. So what's the nonlinear sigma model? It basically starts from the theory developed by Shivaji and co-worker for the 90s. Within a single churn layer, you can describe the problem by a pseudo spin. And then there's some stiffness that it wants to be constant as a function of space. And then I just take 2 copies of that, one nonlinear sigma model in each layer. By hand, we just put in the anti-ferromagnetic coupling between the 2 layers. And then it's very important to note that, as we said, the skyrmion density, this term here, induces a charge density. And so we need to let that interact with the Coulomb repulsion. So that produces this weird n term in the nonlinear sigma model. So here's first the intuitive picture for why the skyrmions are able to pair. So if you make a large skyrmion, the elastic part of the energy is actually scale invariant in 2D. So in terms of the elastic energy, it doesn't really care how big it is. But because the skyrmions induce a local charge density, the Coulomb repulsion wants to just make really big skyrmions. And if the size of the skyrmion is r, the Coulomb energy is basically going down as 1/r in that case. So this is the physics that was worked out by Shivaji and others. But this attraction term scales differently. The attraction term just has units of like 1 per area. So as the skyrmions get large, it doesn't get small, it actually grows. So what this means is that if you make large skyrmions, eventually the J sort of term always wins out over the Coulomb, and that's sufficient to cause binding. So there's a more quantitative description of this in the papers. So what are the results of just numerically solving the nonlinear sigma model? You can just, solve for the lowest energy classical configuration, and then you can measure the difference between this charge 2 skyrmion and the 2 individual electrons. And what you find in the plane of J and lambda looks something like this. You get positive pair binding energy anytime in this red region ensconced in this sort of wedge. This is in units of the Coulomb scale E² over LB, which say in magic angle graphene would be 20 MeV. Okay, so why is the lambda bad for it? You can see that for lambda equals 0, you actually get a pair binding energy down to arbitrarily low J, and lambda is kind of bad for it. Well, what lambda does, remember lambda was an easy plane anisotropy. And what that does is that actually deforms skyrmions, which are SO3 symmetric objects, into merons. And when you deform it into merons, that ends up costing a little bit of elastic energy. And that leads to the easy axis deformation, eventually breaking apart the pair. Okay, but what about DMRG? We can just throw that model and individually compute the energies of these different eigenstates and compare them. And we indeed find, just like in the nonlinear sigma model, that you get a positive pairing gap anywhere in this wedge-like region in the J lambda plane. So again, this is in units of the Coulomb scale, and you can see for J is equal to 0, you get, sorry, lambda is equal to 0, you can get gaps as large as 0.3 of the Coulomb scale. So we get basic agreement between the nonlinear sigma model and the actual DMRG eigenstates. Now you can see one correction here is that the DMRG gives a slightly smaller region, which is favorable for pairing. Shubayu was actually able to understand that quite beautifully. If you go beyond the nonlinear sigma model by including the 0-point fluctuations due to quantum fluctuations, he finds that that increases the energy of the skyrmions in a way that is sensitive to lambda and would bring the nonlinear sigma model phase diagram more in line with what we actually find in the DMRG. Okay, but the takeaway here is the full quantum level. This model has a pairing gap. Okay, but the other thing we need for superconductivity and also to establish what the superconducting temperature would be is we need to know something about the dispersion of these skyrmions, because if they're bosons which are going to condense, the condensation scale is ultimately created by their mass. So there's a beautiful picture for where this comes from, which is the following. So suppose you start out with this bound skyrmion, and then you boost it to some velocity v. Well, what happens is because of the magnetic fields, the charge in the top layer fields a Lorentz force in one direction, and the charge in the opposite layer has an opposite B field, so it experiences a Lorentz force in the opposite direction. So boosting the skyrmion tends to rip apart the two charges in the two layers. But we said that J effectively caused some attractive interaction between them. So as you start ripping them apart, you pay this interaction cost. And if you work that out, what that leads to is an effective mass for the problem. You just get a quadratic band dispersion where the mass is actually set by this Coulomb scale, not the barrier dispersion. Indeed, we started with flat bands, right? There's no dispersion at all, but nevertheless, the Coulomb interaction is able to generate dispersion for these charge 2 excitations. This is actually very familiar from a lot of the physics you might know from quantum Hall effect, for instance, the dipole picture of the composite Fermi liquid. And when we do DMRG, we indeed see we can measure this dispersion relation. We don't have very good resolution because the cylinder is thin. But when we look at energy versus momentum, at least at order of magnitude, we get agreement that there's a Coulomb scale effective mass. We can also see in the DMRG this picture that as you boost it, the two charges get ripped apart by the Coulomb force. So in this bottom panel here, one axis is the distance along the cylinder. And then the other axis is looking at different excited states where the momentum, I'm increasing the momentum of the charge 2 pair. And then what I plot is just the distribution of the physical charge density. And what you see is that for low momentum, the charge when it enters the system just forms a single 2e blob, indicating that they're bound together. And then above a critical velocity, the skyrmion unbinds and you can see the charge just separate into two charge 1 blobs from getting ripped apart by the Lorentz force. Okay, so why superconductivity? We've established the two basic ingredients we need. We have a Coulomb scale pairing gap. We have a Coulomb scale dispersion relation, and that can then lead to condensation. And I won't get into it more, but you can actually quantitatively compare where the pairing gap is observed from where we find superconductivity and rely them on top of each other. They're in quite good correspondence. Okay, so these numerics show that the basic ingredients are there. In principle, this interplay of Coulomb repulsion with a Landau level topology and symmetry breaking actually does allow for skyrmion-mediated superconductivity. Of course, this was the spherical cow model of magic angle graphene. It remains to be seen whether it's actually going to play out once we put in all the details of the real material. But I would say regardless, maybe this is possibly insurance after Andrea's talk as well, like regardless of whether this works out in magic angle graphene, the physics is quite simple. All you have is two time reverse Chern bands with spin, which are tunnel coupled. And if not in magic angle graphene, that could be realized in many other situations. So there's this interesting picture from Andrei Bernovig's group where they realized this sort of physics in a simple lattice model, for instance. So I think it will be worthwhile looking for this skyrmion superconductivity in lattice models, other lattice models as well. Okay, in the final minute, I actually want to, I'm curious, Shankar, did any of this story seem familiar to you so far? I'm going to convince you did part of it already in the 90s. Okay, so just to conclude, I actually want to develop an analogy between the system I just studied in a paper from Shankar and Subir back in '97, where they were studying a double layer quantum Hall system. So it's very similar to what I was looking at. They're looking at a quantum Hall bilayer where both layers carry spin, but they didn't apply this naturally. They were thinking about like actual quantum Hall. They didn't apply the spin flip to the bottom layer, so both layers see the same magnetic field. But then they showed because of the tunneling between them, you get the same anti-ferromagnetic coupling between the two layers that I discussed. And they worked out the phase diagram of this model, and they found two interesting phases. One of them is a nail anti-ferromagnet. So at filling 2, where density 1 goes into the top layer, density 1 goes into the bottom layer, and then their spins anti-ferromagnetically align. Sounds very familiar. And the other phase they find is this spin singlet phase. The way you can think of it is electrons go into a coherent superposition of the two layers. And then you just have one copy of that for up and one copy of that for down, so that overall makes a spin singlet. So this is the much exalted phase of quantum Hall bilayers, which is exciton condensate, because the electrons are going into this coherent superposition of the two layers. So our model differs from this one almost only in a single detail, which is the flipping of the magnetic field.
Mike, could I just add something here quickly?
Yeah, yeah.
You know, there are many of the order of 6 claims of having seen this phase. Most from Japan, but Aaron Pingsik had a paper also. There's a bunch of Science and Nature and PRLs in early 2000.
Yeah.
And I think they're reasonably convincing.
Yeah. So I didn't get into the experiment, but I mean, they were thinking about sets of quantum Hall bilayer experiments as associated experiments here. But in the final slide, I want to relate this model to the model I just talked about. And indeed, there's a mapping. So in the magic angle graphene model, the two bilayers have opposite magnetic field. And then you add electrons to both of them. That's the version of doping. Well, suppose what I do is I take that Hamiltonian and I apply a particle-hole conjugation, taking electrons to holes, but only in the bottom layer. So that does two things. One, it flips the role of doping in the bottom layer. So it takes delta to negative delta, but it also flips the sign of the magnetic field, right? So it makes the problem more equivalent to the one Shankar was thinking about. Now, if you look at the order parameter we are interested in magic angle twisted bilayer graphene, it was a Cooper pair formed between the two layers. But now because I apply particle hole to only one of the layers, that superconducting order parameter exactly maps on to the spin singlet exciton order parameter. So that's the relation between these two models. Exciton condensation in that earlier physics corresponds to superconductivity in the model we were looking at. Now, however, there is a caveat. The models are not exactly the same for the following reason. When you do particle hole, the Coulomb repulsion between the two layers changes sign naturally. So like the model we look at, if we applied particle hole, would give a very weird version of the quantum Hall double bilayer, where if the two particles are in opposite layers, they attract each other rather than repel each other. So you can think of what we've added to the story compared to these earlier studies is that due to the skyrmion physics, you would get the formation of this exciton condensate even if the particle and the hole were repelling each other rather than attracting each other. So that's what I think is kind of remarkable. Even though the topology existed earlier, it's really this energetic detail of how skyrmions are able to lead to these condensate phases. Okay, and with that, thank you.
Okay, thanks, Mike, for such an excellent talk. And now it's open to questions.
If nobody else has a question, Yangzi, may I ask something? I will ask you a question. So, Mike, so this is, I mean, if you didn't have Moiré, would this happen still? Because you need the flat band rather seriously, right? I mean, if you just had tri-layer graphene, let's say, like what Andrea told us, is this still a possibility? I mean, I haven't, I was listening to you, I have not thought through it, but this is the obvious question.
Yeah. So it's a good, so there's two questions. One is the Moiré versus not Moiré. So the role of the flat bands, they don't need to be perfectly flat because ultimately it's the dispersion which actually generates the super exchange. So it's like you need some dispersion to get the T squared over U, but eventually if it becomes too big, you're going to leave this strong coupling picture and something else will happen. And we're working on trying to understand that crossover more carefully. But one thing special about this lambda level picture is this pseudo spin I've been talking about in magic angle graphene is not the physical electron spin, it's this A and B sublattice. Right. And that's tied to the fact that magic angle graphene has 8 bands rather than 4 bands.
Exactly.
In something like Moiré double bilayer graphene, Moiré ABC, or of course ABC without Moiré, you don't have 8 bands. Well, I don't know, at least if I don't consider the annulus, you have 4 bands, right? So you don't really have the same role of this AB sublattice degeneracy. So it's not immediately clear to me exactly whether skyrmions could play a role there because we don't have the right pseudospin space for it to work in. However, moving beyond graphene, there could be a completely different way to realize this physics where the pseudospin is actually the physical electrical spin. The only ingredient you then need is some lattice band structure, which still gives you 2 bands, a churn 1 and a churn -1 band. So maybe this could be realized in non-Moiré systems, but I don't see how to do it in like non-Moiré ABC graphene at present.
So, yeah, thanks. Yeah, so I get it. Thank you.
So could I ask a question? This is Jay.
Yeah. Hi, Jay.
So hi, Mike. So I guess one aspect, this skyrmion type superconductor, one reason that you can think that why this is very feels very unprecedented is that it requires the sort of you have a coherent quantum sort of liquid or whatever, Fermi liquid of some sort of skyrmions. I guess I worry that what's the effect of disorder on this? I mean, in the sense that that's what I imagine is a reason why it's difficult to stabilize or in many cases coherent liquids of these extended defects.
Yeah, I mean, I think so. Of course, the model we looked at doesn't have any disorder, for instance. So while we established that the electrons form these charged 2 bosons, and the bosons do have a sizable mass, well, I mean, one of your worries might be that if these are big things, they just won't move.
Exactly.
But what this calculation shows you is you actually still get an effective mass, which isn't that big. It's basically order 1 in the Coulomb scale. So they don't actually have a hard time dispersing. Now, of course, nevertheless, if you have dispersing bosons, there's going to be competition between it forming something like a boson-glass if there's disorder and superconductivity. And because the model we look at is completely clean, we don't have to worry about that. And sort of as soon as you have the dispersing bosons, they're going to end up condensing. I guess maybe they could form a Wigner crystal at very low densities, but so yeah, I mean, really, you're going to have competition between other phases these dispersive bosons could form, but luckily this effective mass is not some insanely small thing, even though naively they're big textures. I think somehow it's like we have this sigma model picture where they're very big things.
Right.
But I mean, in reality, when we do DMRG, it's still some kind of smallish quantum object. Like it spreads out over a couple magnetic lengths, but it's not like really huge.
It's not like a superconducting vortex or something. Okay.
Yeah, yeah. So I think it's still a quantum object, not like a macroscopic thing. And indeed, if we look at the ground state, the expectation value for the spin is just zero everywhere because it's like quantum fluctuating and so on. It's not some big rigid macroscopic texture.
I see.
So Mike, can I make another comment on this?
Yeah, sure, Shubhai.
So the figure is at like zero density where we are just adding 1 or 2 excitations and checking their sizes. But I mean, once you move to finite densities, then these 2E objects will also have some repulsion between themselves, right? So they won't be very largely extended in space. Like,
I see. All right. Yeah. Thanks. Yeah.
Is there any other question? Okay, if not, let's move to the next talk. And thanks, Mike, again.